All right, everyone. I'm Sam Charrington, founder of TWiML, and welcome to another Solutions Guide Spotlight video. Today, we're going to dig into Sigopt with Eddie Mattia, who's a product manager at Sigopt, which is an Intel company. Eddie, let's get started with some brief background. What is Sigopt?
Thanks, Sam. Really glad to be here. Sigopt is an experimentation platform, fundamentally. A lot of our customers work in the machine learning space, high performance computing space, using it as a tool to kind of manage and optimize their simulations or machine learning model training. So in general, just kind of a tool for modelers to experiment and improve their own ability to maximize their performance and efficiently get to the best models possible.
Awesome. So how does a user get started setting up projects in Sigopt?
So right here, we see the Sigopt Web App. So Sigopt is an API fundamentally. So the way users get access to the functionality I was just talking about, the tracking and the optimization, is through that API, where we also have a number of clients in various languages like Python to make it easy to use the API. But the web app is where you really see the results. So the homepage that we're on here, this will show both individual runs and hyperparameter tuning experiments. In this case, we're going to focus on a machine learning problem today. But as you mentioned, the project is really the kind of the core of most machine learning tasks, where maybe you have a certain data set and a task that you want to build the best model or the best ensemble of models to perform on. So here we see two projects that I have going. One of them is this RGCN project, the kind of neural network that I'm working on. And then another one is for this demo we're going to do today. So let's click into the demo. You can see here I've got some old data that I've archived out of the project, so it looks kind of empty. We don't see any results. But this is the basic project view that you have, where you can see both individual training runs. So in the machine learning case, you can think single set of hyperparameters. And then in the experiments, we also have the collection of runs in an experiment object. So to come back around to the project, you can group runs and experiments, just runs, sort of whatever you want in a free-form fashion as a user can go into this project level.
Got it. And so once I've set this up in the console, I typically access these, the project or the experiments and runs via a Jupyter notebook.
Yeah, that's a very common way that our customers use Sigopt. So especially when you're using Python, Jupyter is a fantastic resource for data scientists to do quick experimentation, which is very much in line with the value that Sigopt provides users. So to get started with Sigopt, you can just simply pip install if you want to use the Python client. We also have an R client, Java as well. And then to actually make sure you're getting access to the API, you're going to need to get your API token. So just to show you quick where you can discover that, once you sign up for Sigopt, you can go find your API token by clicking your name and going to the API token section on the web application, and then setting that as an environment variable. And then all of the Python commands that we're going to see later in this notebook will be accessible to you, and will automatically send those API requests to Sigopt, and we'll log it in your account using your API key. And then connecting this next cell to what you were asking about earlier, the project, we saw that TWiML project, and this is how I'm telling Sigopt, hey, all the runs and the experiments that we're going to see in this notebook, group them into that project that we're using as the demo for today.
Got it. And so tell us a little bit about the demo and the demo scenario that we'll be working with.
Yeah, definitely. So let's just imagine a very standard data science problem. We have the sklearn breast cancer data set. So classic kind of two-class binary classification problem. Where here you can see we're just doing the simple train test split. And we want to build a classifier to perform best in terms of maximizing the accuracy, or later we'll bring in some other metrics into the fold to see how we can get more precise about analyzing the recall and the precision of the classification task. But once we load in this data, what we're going to do is we're going to build an XGboost classifier. So in the beginning of the demo, we're going to see just the tracking functionality of Sigopt as part of this training run. And then once we see how the training run gets logged to the web application, we go look at how that connects to the project discussion we had earlier. Then we're going to extend to hyperparameter tuning. So we'll define a Sigopt experiment, which is the object in the Python client that manages the hyperparameter tuning lifecycle. And we'll see how to execute a few different hyperparameter tuning experiments. But again, we'll start with the run, and then we'll move on to that more complex behavior over the course of the demo.
Got it. And in the run, we've just set some hyperparameter values in the code here.
Exactly. So I guess I'll just get into what the training run object does and what you can do with it a little bit. But your question is really the core of what the run is about. So here we see creating a run with the Sigopt Python client. We're kind of logging some metadata that's associated to this run. So we say our virtual machine is a Colab notebook. We're logging the model type as XGboost. All these things are useful little bits of information that might be relevant to either your future self when you come back and look at this run in a week or a year, or maybe one of your teammates that you want to share these results with if you're on a large data science organization. But then to your question, the kind of the key thing that will power the hyperparameter optimization in the future and is also extremely useful just at the run tracking level is to make sure you're organized about what are the actual hyperparameter values I'm setting. Very often people will start off these new modeling tasks. They'll be changing numbers around. They'll try 10 for max depth. They'll try 40. So you want to make sure you have that all logged and you know which runs were actually performing well against the metrics that you care about. So once you have set the defaults in this training run object, then you can use the run params field and the corresponding keys for the different hyperparameter values that we've set. And you can use them to instantiate the XGboost model. Then we're going to fit the model using the scikit-learn API for XGboost. And then we compute a bunch of metrics to analyze the performance of how these hyperparameters performed. And then we'll log those to the training run object as well. So I'm going to go ahead and execute this cell. Let's see it take a little bit to run.
And then I'm guessing our results are going to show up in the console once they've
Exactly.
posted.
So if we now go into the run, we can see that 9 seconds ago, the run completed, just like you said. We can click into it. And now we can see those values that we set. We saw the next step was 20 that I was playing around with a little bit. And then most importantly, we see the connection between these parameter values and the actual metric scores that we care about. So maybe we're going to use this, maybe accuracy is really our target here. And we want to try and drive this up as much as possible. Or maybe it's a case where we want to trade off the recall of the different tuning sets that we're looking at here. So these will obviously be more useful in the future. We've kind of hinted at the hyperparameter tuning problem to come with the naming of these metrics. But right now we're just doing the logging of this individual run in the project.
Got it. So is the next step to go deeper into the hyperparameter optimization?
Yeah, so that's definitely a common workflow. It's not the only one. There's a lot of modelers who prefer to do a lot of free-form experimentation before they kind of constrain into an optimization problem where they've got a specific hyperparameter space they're tuning in. Maybe they want to add parameters, subtract them without kind of having the constraints of implementing the whole experiment in code. But yeah, to your point, a very common workflow is to then kind of take this same code. So I'll copy and paste that run code up here. And then before I paste it down here, I'm going to show you just a quick import Sigopt. We're going to create an experiment. So this is kind of picking, hey, I want Sigopt to suggest to me now for this run, instead of me hard coding those values, I want you to suggest values in these ranges and use Sigopt's optimization engine that our researchers work on to optimize against these metrics. So in this case, we're just storing a lot of the metrics and we're only optimizing for that accuracy metric. So I'm going to go ahead and create that experiment. And before I paste the run code, we'll just actually verify that in this project, we now have an experiment where all the properties of this experiment object are going to match up with what we defined here in the Jupyter Notebook cell. So now that we've created this object, we can come down here to an optimization loop where we just got a simple while loop going until the experiment lifecycle is complete, which is specified by this budget parameter that we set for the experiment object. And we're just going to create a sequence of these runs now at each iteration of this loop. So we'll notice here that we're inside this context manager where we're using a run created by the experiment object. So we no longer need to create the run like in this line here from above. And we no longer need to set the parameter values anymore. Now, since the run is created as part of this experiment tuning space, Sigopt's just going to drop the values in where we have these run.params dot whatever key the parameter name is. And then also, since we're inside of a context manager, which this is just a regular Python context manager now, we don't have to end the run's lifecycle. That will be automatically intuited. So now we can go ahead and run this loop. You can see it's kind of going step by step. Now we're logging the metrics, and then it should bounce back up to the top of the loop. So you can see we've already got 2 of the XGboost models trained and scored, and we can kind of see the improvements climbing up. This is kind of lucky, to be honest. With only 5 observations, the optimizer can't really learn a whole lot about the parameters and the metrics, but we can see that we've already found some better points than the original one that was sampled. So the notebook looks like it finished, and we can see our kind of progress over these 5 runs here. And then click in and get some deeper analysis on sort of parameters by metrics, plots, even go 3-dimensional if you want to have 2-dimensional parameters on the X and Y here with one of your metrics on the Z axis. You can kind of configure these however you want. There's a lot of analysis available to you in the web app for free, basically.
Mm-hmm. And now going back to where you set up the optimization, in some ways you gloss over where a lot of work at Sigopt has been done. You've not set, this isn't a random search. This isn't a grid-based search. This is using Bayesian optimization and other techniques. Can you talk a little bit about the approach to optimization?
Absolutely. So I'm glad you brought up random search. So there is a way to, if you do like random search, to just kind of drop in type equals random in my experiment object, and Sigopt will just handle that for you. But to your point, one of the things Sigopt has really worked hard on over the years is assembling a state-of-the-art research team in Bayesian optimization and active learning. So Sigopt is doing a lot of modeling in our back end. So not anything on the user's machine. You don't have to host the optimization engine, but on our backend, in order to generate these suggestions when you're doing a hyperparameter tuning experiment, there's a lot of modeling going on to learn the relationships between parameters and the metrics that you're targeting. So in this case, it's a single metric problem where we're trying to increase the tuning set accuracy. So we'll be building models based on techniques like Gaussian processes, tree parsing estimators, and a variety of different Bayesian optimization approaches to kind of quickly zoom in based on this budget, to kind of zoom in by the end of the experiment on the best regions in the parameter space for this task. Kind of to extend your point there, there's also different approaches you can use. So instead of maybe just pure optimization, one thing we've learned a lot over the years is that some data scientists have problems where they just have one target metric, and very often like competition style data science problems like Kaggle and things are structured that way. But very often in industry problems in particular, there's a lot of problems where you might have multiple metrics that you want to optimize for. Right. Or sometimes even more common where you have maybe a single metric or 2 metrics you're optimizing for, but you also have guardrail metrics, constraints where kind of no matter how good you do on those optimization metrics, the points that don't meet constraints on other metric dimensions, really, those points don't matter to you in hyperparameter space. This could be something like a memory size. Maybe you're trying to run inference on a specific device, a specific CPU or something. And if it's too big, if the model is just too big to fit on that edge device, no matter how good the accuracy is, it's really not useful to you. So we spent a lot of time working on making the optimization engine easy to use for things like that. So I'm going to show quickly here how you might think about this, where now I've just set the strategy of the tuning set accuracy to store, like to match all the other ones. But I'm going to go ahead and say, let's put a constraint on the accuracy actually. And then I'll put a threshold. We'll go back to the web app to kind of see what an appropriate threshold might be here. We'll say we want all of the points to be above 0.95. We kind of know that's a good, like a reasonable result for this problem. Yeah. We've seen 3 points now over 0.95. So we can pretty confidently say like, hey, the optimizer should be able to learn that there's points there. And this will direct towards finding points that definitely meet this threshold. And then we can quickly say, let's just try and optimize, make this a multi-metric problem on the different tuning sets. We'll see how high we can drive the recall for both tuning sets. So we'll set these both to optimize. And then one other thing to think about too is like, it's not just the metrics that might be impacting kind of this more advanced experimentation setup, but maybe you have extra information about your parameters. So in this case, we can think of a parameter like a learning rate, where maybe you know that there's values that could be on multiple orders of magnitude that are good values, but you don't really know how to specify the search. So maybe you want the optimizer to search on more of a log scale as opposed to kind of uniform across these like multiple orders of magnitude that we have here. So another thing that you can do is set transformations, like in this case, we'll do log on the learning rate for the XGboost model. And I'll just go ahead and quickly, before I run this, just point out where a lot of this information can get learned about. So if you go into the documentation here, you can see a lot of the standard optimization stuff in our docs, and then also in the advanced experimentation, where a lot of this stuff like apply prior knowledge to your parameter space and advance your metrics comes in.
Got it. And for some additional background, I'd also point folks to a podcast I recently did with your colleague, Gustavo Malcolms, on constraint active search for human in the loop optimization, in which we talk about a lot of the background research that goes into the multi-metric and constraint-based approaches that you're showing here.
Yeah, it's really interesting stuff. And I believe they wrote a paper for ICML last year on the topic. It's pretty short, it's easy to read, and it's really a good explanation of the sorts of use cases where you might want to think about, is it really a pure optimization problem that I'm solving? Or is it more that I have a large set of constraints that I want to find a good solution in, and then kind of do a little bit more of an open search once I know I'm meeting those constraints. So that's kind of like what we're adding to this experiment here by adding the constraint functionality to sort of connect to that conversation you had with Gustavo. So I'm gonna go ahead and create that experiment. So if I go now to the optimization loop, since we've got the same metric space, we just have different targets in terms of constraints and optimization, I'll be able to run this same loop. So now I can click back into the web app and go to my experiments again. And now I'll see that I have a new XGboost experiment. And you can see that instead of just having one value that's getting returned now for the metrics, we have two different target metrics that we're measuring here. So let's see as these results come in. So one thing to note about these multi-metric experiments, we only have a few observations here, but one thing to note is you'll see some points pop up in orange. This point's actually popping up in gray, which means that it didn't meet our accuracy threshold. So this is kind of that constraint active search showing like, hey, no matter how good this point does on the tuning set 0 recall or tuning set 1 recall, the accuracy wasn't above 0.95, so it's not an interesting point to us. Yeah, here's now a better opportunity to explain. These orange points we are referring to as the Pareto Frontier. So this is a common concept, but it's basically an expression of the trade-off between these two metrics in the multi-metric space. So you can see the blue points and these gray points. We're always finding a point on the orange curve. So since there's only two, it's kind of weird to describe it as a curve. Yeah. But if we had more observations in this experiment, it would be more densely filled out. And we'd be able to see that any blue point, we can always find a point that's better, at least the same in one dimension and better in the other one, or more likely better in both dimensions for an experiment with a little bit more data. So yeah, that's pretty much the multi-metrics, the gist of the multi-metric and constraint active search experimentation. That makes sense, Sam?
That does. Now, I think you're primarily running all of this on a single machine. Is that right?
Yeah, that's right.
So if you want to scale it up, what's the approach that you take?
Yeah, so in this experiment specification, we're only running with a parallel bandwidth of 1. But Sigopt, one of the things that's really powerful about Sigopt, especially it being a centralized API that you can send API requests to from anywhere with an internet connection, is that you can run on a bunch of different virtual machines. So maybe you have 4 virtual machines available inside your own cluster, and you have 4 EC2 instances on AWS or something. So I'm going to go ahead and just show something that I kicked off before we started the demo. In this command line terminal that I have up here, you can see I'm logged into an EC2 instance here. Same thing over here, same thing over here, same thing over here. So I got 4 virtual machines running on AWS Cloud, and I'm training some neural networks. So you can see kind of the classic metrics that spit out at each epoch of neural network training on these virtual machines. And these training loops are all going on. And we can see here an example of one stopping. So this neural network we early stopped on this 3rd machine, logged the run back to Sigopt, and then we started a new run and kept going. So that experiment, I believe, is also on this same account. Yes. As you see that 2 of these runs have come in. I think a couple of them actually had machine failures. So that's another nice thing about doing it this way, is you can use the dashboard, this experiment dashboard, actually more accurately, the runs that are a part of the experiment, those dashboards, to do some debugging as well. So you can configure to kind of log the stack trace back to Sigopt, so you can see in this web app next to your quality results what happened on the machine, where maybe there's an out of memory error, or all the different sort of issues that can go on when you start doing data science on big cloud environments.
Got it. And in this case, you're just running kind of simple instances in AWS, but you also, meaning Sigopt, you've got an orchestrator tool that lets you do this in a Kubernetes type of environment if you've got a full DevOps or MLOps team that you're working with.
Yeah, exactly. So kind of the idea behind this orchestrate tool is to make it easy for maybe a smaller team, maybe a larger team, but anyways, a team where you have data scientists that want to do large training jobs, the kind that require very large cloud instances, and you want to do training in parallel. So the Sigopt orchestrate tool, like you said, wraps around Kubernetes. So you'll need a Kubernetes cluster to use it. If you're on AWS, the tool can create a cluster for you, which is very convenient. But if you also have your own cluster, you can pass the kubeconfig to the cluster connect command and get running there. But basically what the cluster tool allows you to do is kind of define Docker files, define your model files, and then use those Docker files to instantiate Docker containers in the nodes of the Kubernetes cluster. So all this model training that I'm doing, like you said, the model training that was happening in those like individual EC2 instances that I was doing, you can have the cluster just manage all of that. So instead of opening up 4 windows in your command line, you can just have one command that you execute where you say sigopt cluster.optimize basically in the CLI.
Got it. Going back to our discussion about the optimizer, my impression is the traditional Sigopt user would be really relying heavily on Sigopt's optimizer, but more recently you're allowing folks to use other optimizers. Can you talk a little bit about that?
So one thing that we've been focusing on lately too is making the tool more accessible to data scientists who maybe have different preferences for other tools. Maybe they're already very comfortable using a tracking tool that's different than the Sigopt runs functionality we showed. So kind of the iteration of the loop. Maybe they want to use something like MLflow, or maybe they want to use a different optimization approach. For a lot of problems, there's a lot to be said for a less general solution. So maybe an evolutionary strategy is much more appropriate for certain use cases. Or maybe if you actually do have access to like 10,000 machines at once, you can just run a random search. It's definitely going to be more efficient in that case. So one of the things that we've been thinking about lately is this concept that we're calling bring your own optimizer. So right now, the functionality is basically like allowing these run objects to be very easy to track the iterations of optimizations done with something like a random search or a custom grid search or a different Bayesian optimization tool. Like here we have examples for HyperOpt and another very popular tool from Preferred Networks, a Japanese company called Optuna. Another very cool package that has a lot of different approaches to Bayesian optimization. So basically, we don't want to try to box people into you either get all the functionality of Sig Opt or none of it. We want to make it easy for people to kind of use a holistic approach for tracking and optimization that allows you to, if you want to compare, or if you want to even just try out new things for a task that you don't know well, or you do know very well, and you have a specific optimization approach that you already know is going to be better than a more general solution.
Right. Can you talk a little bit about some of the use cases that you see customers pursuing with Sigopt?
So the two that we went through today, I'd say are pretty representative of the machine learning community, which is a big slice of Sigopt's customer base and who we build for. So definitely like data science use cases, training models like XGboost, other ensemble models like GBM, CatBoost, that sort of thing. All the scikit-learn models, also very common things that are optimizer tunes. Neural networks, of course, very, very popular in that community, where also the thing about neural networks that I think is a common use case for Sigopt is the importance of tracking those very expensive training models and making sure that when you're optimizing them, you're not just kind of randomly trying parameters. It can get very expensive very quick if you don't have a more targeted approach to tuning neural networks, I guess is the point there. And another big community, in addition to machine learning, that Sigopt pays attention to, and we have customers that use Sigopt for, is kind of the high performance computing simulation world. So a lot of people doing physics problems, biology, things where you have sort of back testing ability. So finance as well, of course, traders have similar problems where you want to run a large simulation and you have parameters that actually influence how the simulation steps through time. And you want to kind of understand how, when I tweak those parameters on the simulation, how does that affect the score that's the output of my back test or whatever I use to kind of assess the quality of the simulation.
Got it. Awesome. Eddie, thanks so much for walking us through the tool.
Yeah, it's really, really good to be with you, Sam. Thank you for your time.